In science fiction, a replicator is a device that can materialize complex objects on demand, right out of thin air. You ask for a part, and the machine builds it from nothing. For centuries, our actual reality has looked a lot more like this. If you wanted a custom, precision part, you relied on subtractive manufacturing. You started with a solid block of metal or wood and used heavy industrial tooling to carve away whatever you didn't need. The core flaw of the subtractive method is visible on the shop floor. Carving a complex shape out of a block leaves behind a massive pile of industrial waste. To create custom parts cheaply and on demand, without heavy machinery or excessive scrap, manufacturing had to abandon the subtractive approach entirely. We needed a way to build from zero. This side-by-side diagram illustrates the alternative. Instead of carving a block down, additive manufacturing builds an object from the ground up, stacking flat, horizontal lines on top of each other. The physical embodiment of this technology is the modern 3D printer, like the Bamboo Lab A1. Instead of using cutting tools, it takes a long spool of rigid plastic filament, typically polylactic acid, or PLA, and melts it into precise patterns. There is no magic to 3D printing. It is the mechanical process of constructing physical objects one microscopic layer at a time, using only the exact amount of material required. A printer cannot understand a standard three-dimensional shape on its own. A slicer software must first cut the digital model into thousands of flat, two-dimensional geometric planes. It then translates those planes into G-code, providing exact mathematical coordinates telling the motors exactly where to move. With the code ready, the physical machine prepares itself. It automatically probes and levels its build plate to guarantee perfect alignment before a single drop of plastic falls. A motorized tool head pulls the rigid PLA filament from the spool and heats its internal nozzle to a blistering 220 degrees Celsius. The slicer has successfully converted human imagination into rigid robotic coordinates, and the machine is now primed to execute them. The printing process is driven by stepper motors. Unlike regular motors that spin continuously, stepper motors rotate in highly precise, measured increments as they read through the G-code. The X-axis toolhead slides left and right over the moving Y-axis build plate. After drawing a solid boundary, it adds a 15% density geometric infill for structural strength. Finally, the Z-axis drops the plate slightly, and the precise layering process repeats directly on top. A 3D printer is essentially a highly precise 2D printer, endlessly stacking its drawings on the Z-axis until they form a physical three-dimensional object. This system hits a physical limitation when a design requires overhangs. You cannot extrude melted plastic into thin air. Gravity will pull it down. Look at this photo of the gateway arch under construction. Engineers built a temporary truss to support the massive unjoined halves, preventing a total collapse. The slicer software applies that exact logic. It automatically generates fragile, tree-like supports underneath overhanging plastic. Once the print is finished, you simply break the scaffolding away. To print in multiple colors, the A1 uses an automatic material system, or AMS light. When the code calls for a new color, a motor cuts the current filament, retracts it, and pushes a brand new color down the tube into the hot end. But the nozzle still holds melted plastic from the old color. To prevent the colors from mixing, the tool head moves to the side and purges the old filament out, creating tiny clumps of waste informally known as printer poop, before returning to the model. By automatically building structural scaffolding and cycling through different materials, modern desktop machines bypass the geometric constraints that limited early consumer manufacturing. The A1 is known as a bed slinger because it rapidly throws the heavy build plate back and forth. When printing tall, heavy models, that rapid momentum limits printing speed and introduces physical wobble. Upgraded machines, like the Bamboo Lab X1 Carbon, solve this through architecture. They feature fully enclosed chambers to lock in heat and control humidity, and use LiDAR scanners to check layers from microscopic errors in real time. This split-screen graphic demonstrates the Core XY mechanical advantage. Unlike the bed slinger on the left, the Core XY model on the right keeps the build plate completely stable, moving only slowly up and down. The rapid movement is handled by the lightweight tool head zipping above it. Stabilizing the heavy printed object and strictly controlling the ambient climate allows additive manufacturing to scale up to higher speeds and handle high-strength, industrial-grade materials. Traditional assembly lines excel at making millions of identical objects, but if you need one highly specific, customized part, massive industrial tooling is useless. Today, additive manufacturing handles extreme bespoke needs. NASA prints highly specific replacement tools for astronauts millions of miles from Earth, and engineering firms use massive automated nozzles to lay down concrete layers for custom housing. By mastering the mechanics of building layer by layer, 3D printing has decentralized production. The power to design and materialize physical objects now sits on a desktop, entirely within the hands of the individual.